Hi everybody. So this is the final section for this chapter. It's about electronegativity and the polarity. So far we've been talking about ionic compound and covalent compound, ionic bonding, covalent bonding. However, for example, like talk about sodium chloride, right? So it's a typical ionic compound. However, it's not like 100% ionic, but it's majority ionic. So maybe it's for example, I don't know the exact number. So maybe 50%, 95% ionic, and 5% covalent. Right? So basically, it's not pure ionic. It's just majority character of this bond is ionic. So 5% covalent maybe. Another example, maybe carbon dioxide is typical covalent compound, but it's not 100% covalent. Maybe 95% covalent. 95% covalent, but 5% ionic. But why it's like that? Because we talk about ionic bonding theory and covalent bonding theory. Those are all theories. So we talk about, at the beginning of this year, we talk about all the scientific theory. We just use theory to explain phenomena. So we can easily to study those natural phenomena and explain like we can use ionic bonding theory to explain why sodium chloride, when it's dissolved in water, is a good conductor. However, carbon dioxide, if you dissolve in water, is insulated, it won't conduct electricity. So we can use the theory to explain it. So in real world, so it's not really like we talk about carbon dioxide like that, right? Double bond. In real world, there's no really bond, not like you use a rope to tie a carbon and oxygen, use rope to tie carbon and oxygen at both ends, then carbon and oxygen bond together. No, not really like that. In the real world, just a carbon atom and oxygen atom get closer. So when they get closer enough, all kinds of forces hold them together. So they start to move around together. So we say they become a bonded compound. There's no really bond exists. It's just all kinds of forces hold them together. Right? Right, so this section we're going to talk about atomic attractions for the electrons, electron distribution, something like that. Right, so we briefly mentioned the electronegativity before. So we talk about a little in detail about what's electronegativity and what's polar and non-polar bonds. So what the difference is non-polar and polar covalent bonds, and another concept is polar and non-polar molecules. There's a little bit difference between this we'll talk about. And what are the characteristics of covalently bonded compound? Basically, the percentage of covalent. Basically, so what's the percentage of covalent, and what's the percentage of ionic for a covalently bonded compound? Something like that. Right. So electronegativity, we talk about this, it's about electron affinity, basically element, how strong element can attract electron. The tendency of how strong, like we have fluorine. Fluorine has the highest, it's a number, 3.98, highest number of electronegativity. This means with all the elements we know, fluorine has the highest ability to attract electron. Noble gas not listed here because usually noble gas won't form a compound, so it's not listed. So basically, almost all the elements, they have assigned the electronegativity number. This is a number, small number below the element. This is the value, electronegativity value. So we can compare this. So highest value is fluorine here. It's the highest in periodic table. And lowest here is the lowest. So what those electronegativity value means? This means fluorine has the highest ability to attract electron, and FR has lowest ability to attract electron. Basically, FR has highest possibility to lose electron to any other element. Right, so this is about electronegativity. Right, then we can compare the electronegativity difference to figure out the bond character. Basically, how much the bond is closer to ionic or closer to covalent. So if the difference, remember on the previous slide we talked about this number of electronegativity. You just compare two, like F fluorine is 3.98. FR is 0.7, so the difference between two higher than about 3.2, higher than 1.7. So if fluorine and FR form a compound, this bond mostly is ionic. So if F and FR form a compound, it's a bond. So this bond is mostly ionic. So if the electronegativity difference between 0.4 and 1.7, because it's polar covalent, we'll explain what the polar covalent means. Basically, it's covalent, majority covalent, however, it's polar. We'll explain polar on following slide. So if the difference is less than 0.4, we'll say it's mostly covalent. If the difference zero, like oxygen gas, nitrogen gas, is diatomic, the same element form a bond. So the electronegativity difference zero. So it's just non-polar covalent. It's just 100% covalent. Okay, here is the graph. If we can study many, we can just study many we can study many compounds. So like we talked about on a previous slide, nitrogen gas is pure covalent, so it's 0% ionic character. So this one is ionic character versus electronegativity difference. So basically it's below, so here 50% line, below 50% line majority covalent. It's above 50% line is majority ionic compound. So we can see the like nitrogen gas, ALP, HCl is a typical covalent compound, and calcium oxide, magnesium oxide, sodium bromide, those are majority is a typical ionic compound. However, you can see the only diatomic, like nitrogen gas, is pure covalent. Other than that, it's just all those compounds have a percentage of ionic and a percentage of covalent. So this we talk about the bond, not 100% ionic or covalent. It's just in between, have percent of this and percent the other. what's polar covalent bond? This means unequal sharing of electron. So what that mean? Equal sharing just like a nitrogen gas, equal, because it's diatomic. Electron shared equally between two nitrogen gas, a nitrogen element. However, like in water, if you compare electronegativity number, oxygen, the electronegativity value much higher than oxygen. So this bond is basically a shared pair of electron, right? So the pair electron closer to oxygen, a little bit further from oxygen, something like that. If you have two electron, so this two electron closer to oxygen but further away from hydrogen. So this two electron. So that's what we so-called unequal sharing of electrons. So electrons closer to one element than the other, or one atom than the other. Right. So for polar covalent bond, we have a, it's called dipole. We're dipole here. So we have a physical quantity called dipole. We can use dipole to measure the polarity of a covalent bond. So basically, it's about electron distribution, electron more closer to one atom than the other, closer to one than the other. So basically, kind of give you a partial charge, not real charge, partial charge at one end than the other. It's called dipole. So we use the delta. So this one is Greek letter delta. Delta plus means partial positive. It's partial positive, not real positive. So delta negative, it's partial negative. So this example like hydrogen chloride, right? So because chloride has a higher electronegative value than hydrogen, so the electron more closer to chlorine than the hydrogen. So we can draw this this called arrow, dipole arrow. This is a dipole arrow. Right? So dipole arrow start with the positive end. So here is positive end. So it's from positive to the negative. So this part is positive. So this end is negative. So draw from positive end to negative. So this arrow end is like a plus sign. And the arrow, the tip of arrow like a negative sign. Can memorize, try to memorize it this way. So it's delta plus to delta minus. So the typical electronegativity value for chlorine is 3.16. Hydrogen only 2.20. So the difference is 0.96. It's in between 0.4 and 1.7, right? In between of this. So we call it polar covalent. It's the value for polar covalent. So you can use dipole to represent a polar covalent bond. You use dipole. So covalent bond, either polar or non-polar, is kind of in between. So polar molecule, if you put a non-polar molecule in electric field, they won't be attracted by electric field. However, polar molecule, if you put in electric field, they're going to align with electric field. We'll have a animation on the following slide to explain what's this align with the electric field, how it looks like. On the following slide, we'll explain this. For example, we can have two molecules of water and carbon tetrachloride. So water is in water we have OH bond carbon tetrachloride have carbon chloride bond. Both bonds are polar. So you can use the electronegativity value difference to figure out it's a polar. So because the difference is between 0.4 and 1.7, between these two numbers. So both bonds are polar. Then the first thing we need to figure out is a bond polar and nonpolar. In case of both polar, the next step we need to figure out the molecular shapes. We use whisper theory. So on the previous section we learned. So we need to figure out which one water or carbon tetrachloride, which one has a asymmetric or symmetrical geometry. So for water, molecule, something wrong here. For water molecule, so we learned from previous section, water molecule is because of this two lone pair electron on oxygen. So water molecule is asymmetric. So water molecule is asymmetric. So it has a definite. So oxygen we can put is so we can put a delta negative on oxygen and delta positive on hydrogen. So we can draw a dipole. Basically, you can draw a dipole this way, the whole molecule. So hydrogen part has a partial positive, oxygen is a partial negative. So we can draw a dipole from a hydrogen to oxygen. However, for this carbon tetrachloride is a tetrahedral structure. It's a symmetrical structure. So carbon, we have a chloride. It's a tetrahedral. You guys did this simulation. So tetrahedral structure is symmetrical. Right? So the geometry is symmetrical. So the electron, basically the symmetrical structure balance out all those polar bonds, make it the whole molecule is nonpolar. So the whole molecule is nonpolar, although this carbon chloride bond is polar. This bond is polar. However, because the geometry is nonpolar, so the molecule become nonpolar. Right. So this can show you this simulation of how this. Right. So if you have if we have put this nonpolar molecule, a polar molecule in electric field, it's going to align in electric field. So all the partial negative going toward this positive end of electric field, and the partial positive going to facing a negative end of electric field. So I can play this. Try to play this again. If you put this in electric field, going to all align. All this, all the molecule aligned this way. Basically, kind of organized way. However, if we put something like okay, the example, carbon tetrachloride. If you put a bunch of carbon tetrachloride in electric field, it just it won't align. It basically could be facing any direction. Right. So how to figure out a molecule is polar, nonpolar. First step, a polar molecule must have a polar bond, like in water. Right? The bond has to be polar. Then we figure out the symmetry of a geometry of a molecule. Determine the geometry. If the geometry is asymmetrical. So the geometry must be asymmetrical. So asymmetrical. So what's symmetrical? Symmetrical like tetrahedral is symmetrical. Those are symmetrical. Octahedral, those are symmetrical. Or like a planar trigonal, this is symmetrical. I can pull up this. Let me finish this slide and I will pull up this ESP Vesper. We have this table. So explain which one is symmetrical. It'll be later. So symmetrical shapes are those without lone pair on central. Without lone pair on central. Like without lone pair, like we talk about this tetrahedral, like carbon tetrachloride. Central is carbon, on carbon is no lone pair. However, water is polar because water on central oxygen is a two lone pair. So we can figure out this way. So whichever one has a lone pair electron on central atom, so those are asymmetrical. With lone pair, those are asymmetrical. Nonpolar is without lone pair. So tetrahedral, trigonal, planar, octahedral, put it here too, linear, all those are nonpolar. All those are no lone pair, not exactly. All those examples are nonpolar because all those are symmetrical. With lone pair on central atom and not symmetrical. Most time with the lone pair on the central atom, this asymmetrical, they become polar, like on water. Okay, I can go back to this Whisper. Oops. Right, so we can use this one to explain which one is symmetrical. Okay, those are symmetrical, linear we talk about. Trigonal, planar is symmetrical. Tetrahedral is okay, actually all those shapes are symmetrical. All symmetrical. So you need to have a lone pair on central atom here with a lone pair is become asymmetrical. For example, we have water. All those with oh no, this is not water. Water is this one. This water has two lone pair, so this become asymmetrical because lone pair substitution. I think this one, although this one has a lone pair, however, is symmetrical. This is symmetrical. This one is symmetrical too. Although they have lone pair, but you don't worry. You don't need to worry about it. You don't need to know what's this. What's example like that. So majority, if there's no lone pair, it's all symmetrical. If there's a lone pair substitution on central atom, become asymmetrical. Those are polar. Polar molecules, those are nonpolar. If there's no substitution, all those are symmetrical, nonpolar. With the lone pair substitution, polar become asymmetrical. Right? Right, some examples here, like water. If you compare this oxygen water, compare the electronegativity value. So oxygen higher electronegativity value, so is the delta negative. It's partial negative charge on oxygen, partial positive charge on hydrogen. So we have a polar bond here. So the whole molecule, because there's a lone pair substitution on oxygen, so the molecule become a polar molecule. This example, carbon tetrachloride, because it's no lone pair substitution on carbon, so it's a symmetrical geometry, so this is nonpolar. This is nonpolar. Okay, this ammonium. The bond is a polar bond because the difference of electronegativity value higher than 0.4. However, it's a lone pair substitution on nitrogen, so this one become polar. Right? So you can simply use a lone pair substitution if there lone pair substitution on central atom node to figure out this polar molecule or nonpolar molecule. Right? Is it polar? So do those practice in your notes and show me your notes. You should have those practice. Try to figure out. So what you need to do, just try to figure out this Lewis dot structure first, then figure out the whisper geometry. Then you can figure out is polar or nonpolar. Do those in your notes and show me those practice in your notes. After you send me notes, I'll explain how to figure out this polar or nonpolar. So this is a physical property of the polar covalent compounds. So their solubility, the most time so solubility is the property of substance ability to dissolve in another substance like salt water. You dissolve sodium chloride in water, right? So this solubility, how good sodium chloride dissolve in water, or it can dissolve carbon dioxide in water. So this soda pop, right? Soda pop is water, basically carbon dioxide dissolved in water. So this is solubility. So polar molecule are ionic compound substance usually dissolve in polar substance like water. Water is polar. So sodium chloride is an ionic compound easily to dissolve in water. So nonpolar molecule dissolve in nonpolar substance. This is called like dissolve like. Like dissolve like. Most time you can use this one to explain it. Like dissolve like. Basically, if the solvent and the solute have a similar polarity, if the polar dissolve in polar, non-polar dissolve in non-polar, so like dissolve in like. Alright, this is a more property of covalent compounds. So covalent compound usually the bond is strong. However, the attraction between molecules are weak, like carbon dioxide. So carbon dioxide intermolecular. So between the molecules, the attraction between molecules are weak. So that's why carbon dioxide is a gas, because the attraction between molecules is weak. So they're harder to attract each other. So they exist in gas, I mean in the room temperature, normal temperature is in gas phase. However, like sodium chloride is the bond between the, so we talk about like ionic compound, actually is one sodium bond surrounded by a bunch of chloride ions. So the attraction is not a good example. Like water, probably water. So water, why is water is a liquid phase? Because its attraction stronger than carbon dioxide, because it's a polar bond. So weak attraction between a covalent compound, also called van der Waals, is a name. I believe is from Holland, person from Holland. Van der Waals forces. So there are three basic typical kinds of van der Waals forces. So we'll explain on following slide. So those van der Waals forces vary in strength. So they have those three types of van der Waals forces has different strength. However, all the van der Waals forces are weaker than the bond, like water bonds, for example, right? So this chemical bond, weaker than chemical bond, are ions in ionic compound like sodium chloride. So the van der Waals forces are weaker than OH bond, or weaker than sodium chloride bond. So this kind of very weak strength. So majority van der Waals forces exist like in you guys study the biology in freshman year. So majority in the biological molecules is van der Waals forces like hydrogen bond. Okay, so we'll explain. So this three typical types of van der Waals forces called dispersion force. We'll explain what's dispersion force. Okay, this is three types. So first one is called dispersion force or induced dipole. Second one is called dipole force. Right. Third one is the most stronger one is hydrogen bond. So we'll explain more in detail. So what's this dispersion force? This is between nonpolar molecules. Dispersion force, like between oxygen gas, between oxygen gases, called dispersion forces or induced dipole. We'll explain in detail what's the induced dipole. Dipole force, like between water molecules. Oh no, not water molecules. Not water molecules. Like dipole force. Probably I'll figure out more example. So hydrogen bonds between water molecules. Between water molecules, hydrogen bond. So between all these three, hydrogen bond is strongest. And the nonpolar, the dispersion force is the weakest. Right? So the dipole force is in the middle. Hydrogen bond strongest, nonpolar dispersion force is the weakest. The dipole-dipole is in between, in middle. So the weakest van der Waals forces called dispersion force. Okay. Dispersion force is dipole interaction. I'll explain on the next slide. So you just need to know now is the weakest van der Waals force. So those dispersion forces most time is between nonpolar molecules like diatomic. We talk about diatomic is nonpolar because the electronegativity difference is 0, right? Because the same atom, so it's the same electronegativity value. The difference is 0 with nonpolar molecules. And the dispersion forces is also depend on number of electrons. Majority of the time, the valence electrons. So it's a bigger molecule has more electrons, the force becomes stronger. So what happens here is, so we can compare fluorine and iodine. So if we in a molecule like FF, I just put it here, it's electrons, right? Iodine, some more electrons, maybe bigger. So the electron can go further away for the iodine. Electron go further away from nucleus. However, in fluorine gas, electron closer to a fluorine. So when this molecule move around, when the molecule move around, the electron not evenly distributed. For example, it move this way, so electron distribution something like that probably. There's less electron on the moving direction, more electrons. There's more electrons at trading further away when the molecule moves this way direction. So what the effect of this? You have nucleus here, positive charge here, negative charge on the tailing end. So basically create a temporary dipole. It's a temporary dipole. So more positive charge at this end, less negative, more negative charge at this end. So it created a dipole. However, it's not permanent dipole. It's kind of a instantaneous dipole or temporary dipole. So that's the origin of dispersion force. Temporary dipole between, for example, you have two iodine molecules. The temporary dipole can interact with another temporary dipole. So it's the origin of dispersion force. So it's because the electron distribution is not even. Because molecules like keep moving. They won't like human being just sit in the classroom. You just sit there. No, they keep moving. The molecule keep moving. They never settle down. So the distribution of electrons is not even. They create a temporary dipole or instantaneous dipole. So there's going to be, because it's an instantaneous temporary dipole, there's going to be a force between a dipole, temporary dipole, with the origin of dispersion force. Okay, here the animation to show you what's happening. So when this hydrogen gas moving around, creating a temporary dipole. So now the hydrogen molecule also moving around, also create a temporary dipole. So these two temporary dipoles are going to align this way, going to attract each other. So this positive going to attract to a partial positive charge are going to attract this partial negative charge. Oops. Right? So basically this origin of dispersion force. It's a partial positive charge attract to a partial negative charge. So this create a force between two nonpolar molecules. So this create this origin of a dispersion force. Right? However, some molecules are polar molecules. For example, it's not a good example. Anyway, so you can just use it. This polar molecule, because the bond is polar. This bond is polar because fluorine has a higher electronegativity value. Hydrogen has lower electronegativity value. So this bond is polar. This dipole is permanent. It's always there. So no matter how fast this molecule move around, this dipole is permanent. So this attraction between this two HF molecule, because it's a permanent dipole, it's a partial positive charge going to attract the partial negative charge between these two. It's called a dipole-dipole interaction. It's stronger than dispersion force, because dispersion is a temporary dipole. It depends on how uneven the distribution of electron, unevenly distribution. So basically, this dipole-dipole interaction is stronger than dispersion force. So we can think about this in gas phase. So if you in gas, you have HF gas molecule, which the polar molecule is this dipole-dipole interaction. So last one is hydrogen bonding. It's the strongest within all three van der Waals forces. So it's a general structure of hydrogen bond. So X could be fluorine, oxygen, and nitrogen. So basically, you can have HO here, HO, HO, like HX, HX, or you can have H nitrogen. So this is a dot lines represent hydrogen bond. HN, HN, or HF, HF. However, most times this in liquid phase or in water. No, not in water. In liquid phase, hydrogen bonding exists most time in liquid phase, not in gas phase. Because gas phases are molecules far away apart. So why this hydrogen bonding exists? Because fluorine, oxygen, nitrogen is electronegative, and hydrogen is electronegative value is much less than fluorine, oxygen, nitrogen. So those bonds are very strong dipole, has a strong dipole. So this it's a partial positive charge on hydrogen attracted to this partial negative charge on lone pair electrons. So the origin of hydrogen bonding, because it's lone pair on fluorine, oxygen, and nitrogen. It's also lone pair on, for example, this ammonia. It's a lone pair on nitrogen. So the hydrogen bond is the strongest between the three type of intermolecular forces, like the previous explained is 1, 2, 3 types. From top of weakest to the lowest, hydrogen bonding is the strongest. You can refer to that slide. So the hydrogen bonding is the strongest among these three kinds of intermolecular forces. So many physical properties of covalent compounds due to these intermolecular forces, like for the biological compound, different properties like DNA interaction, DNA RNA interaction. It's all intermolecular interactions, or solubility of DNA, RNA, or protein in water. So these weak forces result in a relatively low melting and boiling point, like carbon dioxide, low melting point. That's why it's at room temperature, carbon dioxide, the gas, or water at room temperature is just liquid. However, for ionic compound like sodium chloride, table salt, right? It's a solid. So covalent compound, poor conductors, like carbon dioxide, they won't conduct electricity. Like ice is a water, basically cool water down into a solid form. So covalent compounds still can turn into a solid, like ice. Water turn into ice cube. So covalent compounds still can, as long as the temperature and the pressure high enough and temperature low enough to become a solid form, it can become a crystal. But the attractions between molecules much less than an ionic compound. Sometimes solid can form solid covalent compound can form this called covalent network solid, that cause a diamond. Diamond is a pure carbon. In pure carbon atom form a covalent network. So diamond is a tetrahedral structure. Quartz, I believe quartz is silicon dioxide. Maybe I'm wrong, but it's a kind of covalent network. Right, that's all for the chapter. So we talk about electronegativity. You can use the electronegativity value to figure out the bond characteristics. How much this bond is a covalent feature or ionic feature, basically polar and nonpolar covalent bonds and polar nonpolar molecules. So polar nonpolar covalent bond, you need to use electronegativity value to figure out the polar nonpolar. However, molecule, you need to use this whisper geometry to figure out is the molecule is polar or nonpolar, and the physical property of a covalent bond, a compound. We talk about all these three types of van der Waals forces, intermolecular forces. I think I need to talk about a little bit more about okay. So this intermolecular, three types of intermolecular forces exist. So for example, in water molecule, so in water, liquid water, all three types of intermolecular forces exist. Because water molecule going to move around, create a temporary dipole also. So all three kinds of intermolecular, okay, go back a little bit. Where is it? Okay, can use this one. So we have this dispersion force, dipole force, and hydrogen bonding. So in water molecule, all three exist. Because water molecule going to move around, create this temporary dipole. So dispersion force exists in water molecule, and dipole. Because water is a bond is it's non-polar because it's a dipole bond exists in water, hydrogen and oxygen bond. So this dipole force exists. Also, hydrogen bond exists. So in water molecule, all three kinds of interaction exist. However, in oxygen gas, only dispersion force exists in oxygen gas. Because the bond is non-polar. So there's no dipole force and no hydrogen bond. Came up. Okay, like for dihydrogen sulfide. So this one, both dispersion and dipole force exist. However, there's no hydrogen bond. Because hydrogen bond only exists for fluorine, oxygen, nitrogen. So this dihydrogen monosulfide, this bond is polar, so it's a dipole force, and is also dispersion force exists. So basically, dispersion force exists in all covalent compound. So this one, clear this. So dispersion force exists in all covalent compound. And dipole exists in a polar. If there's a polar bond, this molecule is a polar bond. So dipole force exists. Dispersion. Don't forget, dispersion force exists in all covalent compound. Dipole exists in the polar bond. If you have a fluorine, oxygen, nitrogen bond with hydrogen, this hydrogen bond exists. So basically, if this hydrogen bond exists in the molecule, all three kinds of forces exist. Basically, in water, all three forces exist in water, right? So don't forget that. If you see water, no, there's only hydrogen bond. No, all three forces exist in water. Right, that's all for the chapter.